We constitute the preparation stage for this lesson with stack and heap. An ownership is a set of rules that operate how a Rust program manages memory. All programs have to manage the computer's memory while running. Some programming languages do this with a garbage collector in the background, while in others it is necessary to allocate and free memory by explicitly stating this. Rust programming, on the other hand, does this with its unique ownership model. If any of the ownership rules are violated, the program will not compile. Moreover, no feature of ownership slows down your program while it is running. When describing ownership, I'll make an analogy to better describe it. I recommend that you try to study the ownership rules carefully as you apply our examples. Rule 1. Ownership can be compared to owning a home in real life. If you sign a contract when you want to buy any house, and according to the contract, you are the sole owner of that house. As long as you don't sell it to anyone, the house belongs to you. Similarly, in Rust programming, each value can have only one owner. Rule 2. There can only be one owner at a time. If a contractor tries to sell the same home to two people, it is fraud and will be prosecuted by law. From a similar point of view, each value can have an owner at the same time. Rule 3. When the owner goes out of scope, the value is dropped. In other words, the value is not dropped unless the owner of the value has expired. If you have shortcomings about scope, I suggest you continue after browsing scope. When you drop, the value is determined at compile time. Rust automatically calls the drop function when a variable goes out of scope. That's why Rust doesn't have any garbage collectors. Compilation time is therefore considerably longer. I think we can put up with it among other advantages. The variables in our example are known at compile time and are stored on the stack, so the cost of copying is negligible. Therefore, when we assign with the help of the equality operator, a new value is created on the stack and connected to the second variable we created. String type and string literal will better explain the ownership issue with their different behavior in memory. You can preview the string types by accessing them from the playlist. Similarly, the string literal str data type works fast. In fact, unlike integers, although its pointer is kept on the stack and its value is kept in the read-only part of the memory, it works quite fast. Despite their fast and efficient work, they are not suitable for all situations. For example, in a situation where you ask the user to enter their name, this is not predictable at compile time. You don't want this when you compile the program. The program is compiled, put into service, and when a user who wants to use the application wants to become a member, the second string type of Rust is string. We got an error here because Rust no longer considers S1 valid. When we assign S1 to S2, we copy the string's data on the stack. That is, we copy the pointer, length, and capacity in the stack. We do not copy the data in the heap that the pointer refers to. We said earlier that when a variable goes out of scope, Rust automatically calls the drop function and clears the heap memory for that variable. However, our figure shows both data pointers pointing to the same location. This is a problem. When S2 and S1 go out of scope, they both try to free the same memory. This is known as a double free error and is one of the memory security bugs. Freeing memory twice can result in memory corruption, which can potentially lead to security vulnerabilities. But Rust also overrides the first variable, and this event is known as move. In this example, we can say that ownership has moved from S1 to S2. This solves our problem. Only when S2 is valid, when it goes out of scope, it frees up memory by itself and we are done. Therefore, S1 is considered invalid and Rust does not need to release anything when it goes out of scope. You can use the keywords shallow copy and deep copy to learn more about the behavior of memory here. If Rust also copied heap data instead, it could be very expensive in terms of runtime performance if the data in the heap portion of the memory is large. If you still want to clone the data on the heap, you can use the clone method. As you can see, this time it didn't give an error because the data on both the stack and the heap were copied. However, it is important to remember that this code can be quite costly when using it. They work with the same mechanics in functions. When you enter a parameter in the function that is on the heap, the ownership of the function is now transferred and the value becomes inaccessible when the scope of the function ends. As you can see, we cannot access the variable s after the scope of the function is over. However, this does not apply to types on the stack, such as integers. As in our example, this time the copy property is called. Because the value of our variable x is already kept on the stack and Rust doesn't move on the variable x. Instead, it copies and makes those variables still valid after they are assigned to another variable. If we look at the string type again, we can bind the ownership back to the variable with functions that return values. While this method works for simple operations, it can be tedious to always pass the ownership to the function and bind the value back to the variable. In our next example, we will only find the total length of the string type. As you can see, if we want to reuse the data we have transmitted, it seems quite daunting that everything we have transmitted has to be returned as well. Fortunately, Rust has the feature of using a value called a reference without passing the ownership. Let's explore this feature together in our next lesson.